Hi, I'm Fiona Polack. I'm the Head of Computer Science at Keele. I wanted to give you a bit of a brief introduction into my favourite research areas, which are complex systems and software engineering. Engineering complex systems is something which takes us beyond simple, straightforward software engineering and actually beyond most of what you would cover in a degree course. But let's have a look and see what we can do. So, if we start with some definitions, I use two terms differently. Complex is not the same as complicated. So, looking at a complex system, we'll find a system which has lots of simple components. The components exist at many scales, and we have to run the system to find out what it actually does, what happens. You may think that sounds a bit odd, but actually all natural systems are complex. If you think about a body, or a tree, or flocking birds, which I'll look at in a minute, you see lots of different things happening at different levels, and you see things which appear to the observer, which wouldn't be obvious if you were inside the system. As an aside, we also find lots of manufactured systems, cyber-physical systems, and things called systems of systems, which are complex in their nature. So by contrast, complicated systems are what we often think of as engineered systems, whether that's mechanical or civil, electrical or software engineering. These things are made up of manufactured components which exist on the same scale as each other, so you can simply interface them, and you can predict and even prove what will happen when the systems run. And we can think of the development of a complicated system as normal software engineering or normal mechanical engineering, normal civil engineering. So that's our baseline, that's our normal understanding. If a system's complex, we have to think about different things. We have to think about how to develop using trial and error. So real-world complexity, as I say, is something you'll all be aware of. And in your own time, you might like to look at the video on the right, which is a truly spectacular sequence of starlings flocking. Here, the starlings, the birds, have individual behaviours, but what we as an outside observer see is this amazing swirling, forming, evolving pattern. It's called an emergent flock. And that sort of patterning is very, very common in nature in many, many different ways. Just pushing that example a bit further, you may have heard of Reynolds Boyd's. Boyd is just a bird in a computer. So Craig Reynolds discovered that you could simulate a flock of birds using three very simple rules, three very simple and incredibly easy to code rules. So if our green bird in the middle, or Boyd, is moving to the right, a separation rule says that the other birds will try and stay away from it. An alignment rule says that whilst they're staying away under the separation rule, they'll actually try and move in the same direction as our central Boyd or bird. But then we have a cohesion rule, and the cohesion rule says that actually birds quite like being together. So there's a tendency to move together. So as you put those three rules together, you get birds that don't fly into each other because they're separated. They align, but they also form a cohesive group. So they align and they keep moving close together. And actually we can do some very clever flocking simulations with these three simple rules just by changing things like how a bird perceives other birds. Can it see birds behind it or only birds in front of it, for instance? That I would call a complex simulation. It's a simulation of a complex system in a computer. So when we're actually looking at complexity in software engineering, we see things which are very different to normal software engineering. So normal software engineering would be building things like the software that hangs behind this video presentation, the presentation software, the web software. It would be things like building the systems that run automatic teller machines in banks, ATMs, or the things that record whether you're registered at school and what your attendance has been and what exams you passed and so on. So traditional software engineering engineering what I called complicated systems earlier, we start by asking what's the client want? The user, the client, the person who's going to own and use the software. And then we create a model of a system that can do that. A model's a simplified view, it might be diagrams, text. Ultimately, it's going to be code. And when we get to a code model, we talk about implementing. And you might hand code. If you did a computing or IT course at school, you might have been asked to build some code. Or increasingly, you can generate code from more usable models. You might be creating a database or some other storage system. You're probably going to create a user interface or an interface where different systems get fixed together to interact. You would do some testing of functionality and of performance. You would do some installation. You would check with the client and maintain or replace the system in the long term. However, when we're building a complex system, actually we still do all those things that you do for complicated systems, but we can't plan it in quite the same way. So we have to work out what we can observe. So this system that we're building, say we're going to simulate a flock of birds, what can we actually tell? How do we know that they're flocking? How do we know that our system, when we run it, is doing the right thing? And then we're thinking about, so that's what a flock looks like. Perhaps flockiness is a large number of birds that we can perhaps quantify over a short area. But what are the low-level systems doing? What are the individual birds doing? How do we model each of those birds? How do we code those 3 rules once we've worked out that those are our 3 rules? How can we model that? What do we miss out? So from our Boyd's model, we miss out any sense of the bird as a living being. We miss out the fact that it sits in trees and sings. We miss out that it eats. We miss out that it has baby birds, that it looks after baby birds. We miss out all those things. We just focus on the behaviours of that low-level concept, that bird, which are relevant, we think, to flocking. How do we miss those out? It's an art rather than a science. And then we create a program to do this, and as traditional software engineering can come into that. But we make lots of compromises and lots of simplifications. We need to keep track of those things. Then we need to run our simulation. In this case, if we put a visual front end on it, we can see whether the system is doing the right thing. And then we can tweak it to make the birds flock better or differently, or flock in straight lines, or do swirly flocks. We calibrate and we tune. Very, very different to traditional software engineering, where we would be testing and possibly even improving. And then we can run experiments and see whether we've got a useful complex system simulation. So that's just a taster of what I've been doing. That's the research that gets me out of bed in the morning. If you're interested, if you come to Kiel, or even if you don't come to Kiel, I'm always happy to talk about complex system simulation. So thanks very much for listening.